Okay, we are almost at the end of this discussion. For handover, we discussed the procedure, but see that the loss of data can be avoided here. You say utilizing the interface between the neighboring images, the connection between the source image and the target image. So it's the super. I mean, when we show this figure, see that it says sequence number status transfer. Well, the RC layer or MAC layers are reset handover. So the source image, if you have some RC blocks left, they're flashed. So they cannot take care of the PGUs uh, which are not transferred in the pause period, the period before you establish the new connection at the new cell. I mean, you lose connection to your old cell, and after a while, you establish a new connection. And uh, in the meantime, you you can lose data, but this data, whatever you have in RLC or I mean, they are reset. These layers are reset. But however, the PDCP layer, this layer handles. PDCP layer normally doesn't retransmit anything, but here it takes care of this problem. What it does, every layer has a sequence number, right? I mean, not every, but RLC for PDCP layer, we already showed the header. There is some sequence number to for the other end to reorder. It informs the sequence number that that is the the first one in the pause period, in the period when you have no connection, and then it does it in both downlink and uplink. But let me tell you that this whole procedure is done only when you have error-sensitive application. You have acknowledged mode for RLC operation. If it is unacknowledged mode, then this procedure is not used. It just lets losing the data. Now, when you have acknowledged mode, then say you are it sends a sequence number status or SN status transfer message. The source element sends it to the target element. And after transmission of this message, it starts forwarding data to the target inert beam, as we saw there. Okay, instead of forwarding data to the EV, it forwards it to the target inert beam. Okay, assuming that it no longer has connection with the EV. And it also tells you that what the next sequence number should be in uplink. So it's the SN status message. It gives that information for downlink. For uplink, it includes the information who is PDCP sequence number. It has failed to receive as the first one. It has received properly in the uplink until certain PDCP SN. So in the SN status transfer message, it includes which one is the next, which PDCP SN is the next. So there's the first missing PDCP packet. Okay. It includes the sequence number for that, but it may have some sequence number, some packets received intermittently. So some packets are there, some are not. So it actually includes a bitmap. Okay. It includes the number for the first missing sequence number, and also it includes a bitmap. Okay. That after missing the first one, then some packets may have been received. So which one has been received and which are not? 1001. Okay, so 0 indicates it is not received. So the other side can understand, and if it receives some packets at the other end, it can put them properly, or if it is not received, then it can request. So it fills in all the missing slots. Okay, so the sequence number, according to security sequence number, it confirms complete reception. Okay, that's pretty much. The window size is 2048. If it is the reordering window, I mean, the maximum number, sequence number, in terms of the sequence number, it handles 2048. And see, this message will discuss the RC connection reconfiguration messages like your handover command. This one, RC connection reconfiguration. It includes that message is actually includes something which the target email will be forwarded to the source email earlier. So uh, that part is piggyback on the RC connection reconfiguration message. So the UE comes to know which target email should go, and that information that this one is called mobility control info. That component, that part, okay, piggyback, which has come from target email. That includes what okay, I mean the PCIC. This includes PCI of the target itself. This whole message was actually created by the target email. Okay. The source email is simply forwarded, and the frequency, the bandwidth, it will get a new serenity. That serenity is included, and also the random access. If it is dedicated, then the preamble and the resources are given. If it is not, okay. So if this IE is not included, then the UE assumes that okay, dedicated random access is not possible. So if I is not included, then it performs contention-based random access. So the target in on B sends this one if dedicated random access is possible. Okay, that's pretty much. And please go through it. I may have missed explaining everything. Well, once you have the data forwarding starts taking place from serving it gateway to the new target email. Okay, we'll discuss the next lecture. Mama. We're going to talk about a couple of topics before we begin discussion on 5G. Actually, you know what I need to do? I need to discuss a lot of things, and I need additional classes too. And the relevant thing is that I posted in the morning that your lab quiz cannot be delayed too much. There's some real problems for the lab quiz teachers. So what we can do for you is to exclude the Excel demo from our lab course. Okay, so we will from time to time in our theory classes we'll do some demonstration. So maybe from tomorrow we'll begin, and that will be included in our theory. So good? I mean, what do you think? This is probably the best choice for you. Okay. So, I mean, that will also require some time. So, I need a couple of extra classes. If you all agree, then we can schedule the classes. We don't have to schedule it today. I can talk to Samuel later. Anyway, so we'll discuss a couple of short presentations. We'll now go through, and thereafter we'll begin. I've already uploaded all these things. Most of this discussion I actually did before, so I can go through it quickly. See, there are cells with different capacities, like the large cell are called macrocells. So this can be in the order of kilometers. The cell radius in the order of kilometers. But if you have less than 1 kilometer, then you may call them microcell. Okay. And accordingly, the transmit power will also be lower. But if you install the base station for certain area, okay, say maybe for a mall or campus, stadium, this kind of area, so then you can call it picocell. And if it is if the area is even smaller, okay, mostly for buildings, the femtocells are used. Okay, so microcell, picocell, and femtocell. The typical transmit power levels are also shown here. Uh, this is a figure. Just you have macrocell within the covered area. You can have some femtocells in the building and also some picocells. Now there are sometimes covered holes in the deployment, so you can fill out using this sort of some additional cells. Also in the cell edge areas, um, you you can have some important plants, some cell edge areas, but the coverage is not very good, so you can install additional base stations, that small base station, okay, so picocell or something. Now for femtocell, uh, I mean, you are using it for buildings, but for buildings, we know that Wi-Fi or similar solutions are also available. The major difference is that when you use Wi-Fi, it's available within your building, but as you step out, the same operator can no longer serve you. But if it is femtocell, then if you're a Grameen user, then in your building, you may want to install the femtocell. So it's also a part of your solar, like regular solar system. So your femtocell will be hopefully also be installed from Grameen. From Grameen, you arrange the installation. I mean, for femtocell, the base stations are very small. It's like, I mean, you can hang it somewhere. Okay, it's really very small. And they're connected using some wire solution, most likely. The backhaul, the link that you use to connect your base station is called backhaul. The backhaul can also be wireless in some other frequencies, but most likely it will be some wire solution. Okay, so I mean, so if it is the femtocell instead of Wi-Fi, then seamlessly actually you can have you can move out or move in. Okay. Otherwise, if you are Wi-Fi, you may have also your mobile data on, but you will, I mean, as you change your service from Wi-Fi to your mobile data service, So there will be some packet losses. Okay. There is some film to cell gateway which forwards number of film to cells are connected to the gateway. And another solution for building, okay, well, why do you need femtocell in the building? Uh, Normally we have covered in buildings, right? But in the case of large buildings, commercial buildings, you may not have good signal level deep inside the building. So you may want to install femtocell inside. So you have enough coverage. You can use the cellular services with good quality. So another solution. So the key problem is the penetration losses. Because of the high penetration losses, you may not have good coverage inside building, so you need 10%. An alternative solution is to use distributed antenna system in buildings. In that case, you install a number of antennas at different places and connect them using wires. Okay. So many different antennas distributed at different points in the building, and you use some cables to connect them. So it's again, like your femtocell, you use a single base station, but the antennas are distributed. The signal is transmitted from many different points in the building. So you ensure good covers throughout the building. But of course, this sort of coverage also is done, designed using some prior simulation. Okay, and this is the result from a simulation. I don't remember if I did it myself, but long ago I used some. I used an in-building for several months. I had a license for in-building RF simulation. Okay, I even forgot the name of the tool. This is a popular tool. So it was a simulation using that. I did some simulation. Well, this one, no, this one I didn't do. Yeah, I must didn't do. But I did some simulation, similar simulation I did for some building. Anyway, so simple configuration. But gas is also a popular solution in developed countries. So for buildings, we basically have three different types of solutions. Well, but if you have multiple sizes of the cells coexisting, then it's a mixture, and then it is called heterogeneous network. Homogeneous network means you have the same cell size. Okay. But when you have a combination of a large cell, picocell, femtocell, sometimes large, your small cells are overlaid by a large cell. And an advantage is that if you have high speed traffic, okay, then so those high speed cars uh, can remain hooked up with the large cell so that they don't have to perform handover very often. And pedestrian or stainless steel users can keep using the small cells. How is that maintained? Well, there's hysteresis. Okay. that can actually maintain these things that you are hooked up with the large cells. Switch to this. Now this is the last slide. This one is the well, we discussed some events for handover, like event, say that event A3 is most commonly used to make a decision for handover. Actually, event A3 triggers the measurement reporting, but based on measurement reporting, handover decisions are made. And in the case of event A3, the user compares the signal level between target node B and the surveying node B. Okay. If the target signal is higher by a margin, then it starts sending the report. That margin is called offset, A3 offset. Okay. That margin, and I'm not showing the whole condition, but in the condition for event 3, this is most commonly used. So sometimes it may happen that when you have head nets, you don't, you have macro cells with high transmit power and some small cells with low transmit power. So in that case, the handover condition is fulfilled when you are far away from, you will compare, or actually at the network end, finally there will be comparison. And you will be switched to your small cell when you are very close to that. Okay. But, say you have, just consider that you have a large, a base station with high power and a small cell with low power. Okay. And between them, the distance is 1 kilometer. So when you are at the right at the middle, 0.5 kilometer away from both, then of course the power from the large cell, okay, from the strong base station is very high. So you go towards the small cell, further towards the small cell. And maybe when you are away from the large base station, I'm talking about head nets condition. So when you are away from the large base station, maybe you have gone to 0.8 kilometer. Then the power may have been equal from the small base station, and thereafter the switching may occur. Switch to this. So that's how the very small users, very small number of users may actually get connected to the small cell, and that can often create non-uniform distribution. The large cell may get too much loaded. Okay, the small cell may also have almost equal bandwidth. Okay. So, but the number of users which connect to the small cell is too small because of their power difference. So in that case, what you can do, you can bias. Okay. So you can add in the condition when you compare, you can like the this offset. Okay, so you can play around with the offset and you can bias. So what may happen, say instead of 0.8, maybe when you are at 0.7 kilometer away, okay, your condition, as you set up the condition. Okay. The small cell may get a priority for handover or may fulfill the condition for handover. Okay. So that H3 offset you can play around with, or the network, inside the network, the condition can work with. So that is called cell range extension. That's how for the small cell, the range of the small cell is extended. Okay. According to its power comparison, the coverage area should be very small. But that is, using the handover condition, okay, or the bias in the using bias in the handover condition, you set, uh, you create a larger coverage area for the small cell. This is called cell range extension here. Cell selection offset. That is done in both ideal and connected state. CR is used in both. For cell selection, we already saw the bias option. Okay. Any questions? No. Another quick presentation. This one gives you what you do for we know that for to support different applications, you need different types of bearers. And the bearers are called PPS bearer when you consider them for the when you include the core network or the bearer path. Now, so different types of applications require different QoS, and so you need different bearers. And we also saw QCI. This one we showed you before. For different applications, different QCI are defined for LTE. They have different but delay and error rate, and also priority. Okay, which bearer we prioritize for applications or for data forwarding. Among them, you see IMS signaling. Well, it's something you need when you set up voice call or when you use VoLT. The real IP network or it or voice packets. Then to support voice at the application layer, you need some control signaling, which is called IMS signaling. It's actually not only dedicated for voice, but essentially voice uses. So anyway, different QCI are used for different EPS bearers and different types of application needs. So as I told you before that a default bearer is established when you first power up, and that remains active until you power down your TV. So that default EPS bearer is normally the best effort for web browsing or this kind of applications it is suitable. But if you need VoIP or video, then the QoS requirements are not supported here. So you need to set, need to add some EPS pairs. So these are called dedicated EPS pairs. So two types, default and dedicated EPS pairs. So let's see how dedicated pairs can be established. Well, they can be established either from the network end or the EV can initiate. Okay. I mean, to each side first feels that we need to have data transfer. So that side will initiate. So from if it is created from the network end, then PDN gateway first initiates the because I mean it is for data flow. Okay. I mean, of course, uh, I mean there can be request PDN gateway. It can receive a request from the MME, but for I mean I'm showing only the part of part for the establishment of the radio bearer. So PDN gateway sends request for the creation of the bearer, and then ultimately, I mean MME also sends the request and actually includes the bearer configuration. Okay. Accordingly, P-Node B sends the request and including the bearer configuration, how it is. So this, when it is acknowledged, then P-Node B also sends a response, and then uh, you let's say let's, for the serving gateway PDN gateway part, this is the response. This response also goes to the image. This, this response goes to the this part serving gateway. PDN gateway. So ultimately, I mean for this request, PDN gateway receives the response, and then data transfer can be initiated using this new dedicated EPS pair. So pair establishment is completed here. Okay. Now, this one can take place when you are in RC connected state. Okay. But if you are in RC idle state and say you want to make a call or something, so then or the network comes to know that you need, I mean, you are receiving a call and the network first comes to know about it. So it will then page. If you come feel that you need to make a call, then you initiate random access procedure. But this paging and random access procedure we have explained so far covers only what is happening on the radio access network. But the establishment of the data flow pipe or bearer is also a part. Okay. And until you have that, you cannot transfer data. So that's what you're showing now. Say the EV is initiating. Say you are making a voice call. You are in idle mode, but now you make a video call or something. So first the random access procedure. Then when you send the random RC connection, you know that this is the message. This is message 3, and I mean for RC connection setup, you always use this one as your message 3, and then the network responds. Okay, when there is some HRQ ACNAC which completes the random access procedure, but the network sends as a to complete the RC connection setup procedure. The inner sends a command. Go ahead and set up RC connection, and then you acknowledge. So then this complete means completes the RC connection setup. But when you send this RC connection setup complete message, a message is piggybacked on that for the core network, the service request message. You know, it just forwards, detaches that part and forwards it to the MME. So MME knows that MME knows what to do. Okay, from this one that you need to say make a call, make a voice call or video call or whatever. Then accordingly, okay, it does the need for okay, sense that okay, you go ahead and create the YouTube there and all that. So if you have, I mean, you mean, this is what is done when if you already have a radio bearer which can support your service. Okay. If you need a new uh, bearer, the PPS bearer, then this procedure you need to follow. Okay. Then this procedure will take place. This is what I'm showing for networking. From UEN also there is a similar procedure. Okay. But whichever end it is done, this procedure takes place. But if you have a bearer that can support your application, but you are in IRC idle state, so you have to, I mean, that radio bearer, that EPS bearer was in dormant state. Okay, so you activate it. You come to RC connected state, activate that bearer, and then start using it for data transfer. Then this is the procedure. Okay. Of course, I'm showing it for EU triggered service request. It could also be a network triggered service procedure. Then the early message would be paging. Okay, so when the unit receives this one, it activates the security. I mean, we will discuss this message security mode from RC. So this is the activation of security at the AS. Okay, once it is done, we will send RC connection configuration, which includes the necessary radio setup, okay, for the particular data type of radio pair. We acknowledge that, and just right after the acknowledgement, you can start sending your data. Meanwhile, you also have, I mean, MME also receives the response to that, and thereafter, data transfer and downlink can also start. Okay, so that's pretty much. Now we'll have a quick discussion on voice over LTE. Well, we don't have that yet in our country, but many countries are already using voice over LTE.
Sir, sir, as far as I know that the VoLT service has started in our country, sir, by many network providers.
Commercially?
Yes, sir, I think, sir.
I mean, they were doing tests. I'm not sure if they have already started. You can actually check it. Just make a call, make a voice call, and see if you are still on 4G or not. If you are, then very easy to check. If you switch to 3G network, then it's still CSS. Anyway, if it is already done, then it's fine. It's an improvement. Okay. So in that case, you need I mean, the it configures something called IMS, Happy Multimedia System, which can support voice and this kind of application, which, as you know, voice has a special data traffic pattern, very small packets, but at regular intervals, almost continuous. I mean, there can be discontinuity sometimes. Of course, there can be break. There can be break, especially, I mean, in one direction. There can be sometimes, you know. So, I mean, you need, I mean, this IMS is developed to efficiently use uh, uh, and which also pretty much confirms that you have proper propagation of the voice packets efficiently and reliably. Now, if you start supporting VoLT, then this is not mandatory. Okay, you can have single default EPS bearer as we have explained. So you can set up a dedicated EPS bearer to initiate your voice. But normally when you begin commercial VoLT, what you do is separate, I mean, at the PDN gateway, you can have another point there. These are called access point network, APN. Okay. So it is you can just consider it like a second PDN gateway. Okay. So each of them has a name. This APN has a, I mean, just in letters, in English letters, it includes a name, but also that name associates an IP address. So, uh, so a separate APN is used there, okay, like a separate PDN gateway to support voice, and you establish a second default APS bearer. So when you power up, okay, during initial attach procedure, two default EPS bearers are simultaneously established, and it is always a fact that you can have multiple APNs, but each APN, to connect to each APN, when you are using supporting multiple, when you are using a new APN, you will be connected using another default APS bearer. So that is what is done here, two APNs, and of course to connect it to another APN, you need a separate default APS bearer. So for, I mean, the one that supports IMS traffic, okay, the APN for IMS uses this default EPS bearer with QCI 5, okay, which can, which QCI 5 is good for the control messages for your voice application. I mean, to support the voice packets and additional control messages, okay, uh, are used using some protocol called SIP. SIP is Session Initiation Protocol. I mean, that is invariably used. It is very popular. Okay, let me write down Session Initiation. Popular for voice type of application. So, I mean, when you have some break of packets, okay, pause, okay. So all these things, again, you initiate, all these things are well handled. Okay, I know how it is handled in services network, okay, but we're not discussing that. But here you, so that is, these messages go, SIP messages, okay, SIP messages go over default EPS bearer, but actual voice traffic go over another dedicated EPS bearer. So, and you also have default EPS bearer. So two default EPS bearer, the normal default EPS bearer, okay, to support the regular applications, which I said that is suitable for browser, email, this kind of application. So these, when you create some dedicated EPS bearer, if you have multiple default EPS bearer, then of course that dedicated EPS bearer has to be linked to a particular default EPS bearer. So I mean the dedicated EPS bearer information has a field. Okay, we're not discussing all these fields, but my book has the details. It has a field to indicate which default EPS bearer it is connected to. To establish this default EPS bearer for voice, it is connected to your default EPS bearer 1, which is carrying your head. And you can have other default EPS bearer features for other applications, which will be connected to default EPS bearer 2. Okay. So that is pretty much. And the last slide just says that you don't have VoLT, then you use CSFB. Although there are, I mean, more options, but CSFB has become popular. All right. Questions? Okay, now we will begin 5. Mhm. We're gonna cover from a book. The book name I provided on the course plan. LTE, sorry, 5G in 5G New Radio in Bullets, authored by Chris Johnson. He's from Nokia. I also loved his book on LTE, on 4G. I purchased quite a few books, including his one that is, is the title 4G in 4G in Bullets or LTE in Bullets. So we depicted using bullets. Now, well, the key difference from the early generations of 5G is that when people introduced 3G or even 4G was first introduced, the key motivation or the key force was that we need to provide very high data rate capabilities. A lot of applications emerging with very high data rate support, but we are lacking that capacity. So how we can improve the data. But now the key motivation is little different. Because of this, because of the use for a long period, many different applications have emerged, and they are so diverse. Now there are many different types of applications, and many of them have different types of requirements. So now you have very diverse requirements uh, of your platform or system that you use to provide the service. So your system or whatever you use for to provide the service needs to take on many different structures or, or what should we say type of platform because the type of so they are categorized. Okay, these types are categorized in three classes: EMBB, URL system. Very easy to understand what they actually mean from this pyramid. EMBB is exactly like before, that you have the high data rate requirement, high bandwidth requirement, enhanced mobile broadband. So, but MMTC is, mostly like IoT. In that case, you have many devices and most likely each with very low data rate. Okay, very low data rate. And the delay requirement may not be too stringent. Here, it's various, the delay requirement can vary. So these are two extreme points. But you see, there are many different types of applications now. And some require higher bandwidth, some require lower bandwidth, but there are many in number. Also, there's a third corner, a third type of requirement. So, in some cases, reliability is important. We discussed error sensitive and delay sensitive applications. If you need high delay, then we found that the application doesn't need high, high delay and high reliability. Usually, you don't need. But in this diverse world now, that's another thing to think about: how much reliability you need, and then how much latency or delay you can allow. So then you can also categorize, and all these classes you can actually, all these categories you can put into one class, URLLC. Okay. So mostly high reliability and low latency. You need together. Okay. Unlike the applications of the early days, 2 to 3 days. However, like say when you are using some application to avoid vehicle collision, okay, they are communicating, and or maybe you are controlling a car from a remote place, but there should be quick signaling. Latency requirement is stringent, and also it has to be reliable. Otherwise, there might be collision, there might be casualties. So, but then it could be a question or some automation in the industries. Okay. If there is some erroneous data, then there can be major damage in the machineries. But at the same time, you may have to have quick communication so that the machines, which may be moving at some high RPS, can also cope with everything. Uh, so, so there are also many different categories. How much reliability you actually need, and then how much uh, latency requirement you actually have. Say, mission, there can be some accident, some fire, or some other cases. You need some services, critical services, mission, mission services. So these things are also equality. So 3 types: ENBB, MMTC, many devices, massive, but for I mean they all do machine to machine communication. Okay, so the use cases. Okay, so vehicle to everything is just actually an example of URLCC, automated vehicle. There's high reliability and low latency together. For V2X, it could be V2 vehicle communication, vehicle to vehicle communication, V2 pedestrian, or vehicle to your network, or some infrastructure, roadside infrastructure. So there are different types of V2, so commonly called V2X. The requirements in terms of data rate and say other things also, say how many devices you may have. So for MMTC, there could be something, I mean, minimum value set by 3GPP to declare that you are supporting 5G. So 3G, 4G, 5G, for all of them, there was a set of some minimum values you have to achieve to claim that you are now on 5G. So this is some settings from 3GPP. Although I mean, in the real market, a lot of times operators could not fulfill that requirement, but declared that they are still they have already on 3G or 3.5G or 4G. Okay. So these are some minimum requirements set by 3GPP. So for ENBB, MMTC, it says how many devices you have to support if you want to declare that it is 5G. So to fulfill 5G requirement, these are the minimum requirements for ENBB in terms of throughput, for URLCC in terms of reliability, both uplink and downlink. Okay, now the network infrastructure looks a little complicated, but it is very much similar to 4G network. Okay. You can assume it like 4G. The user equipment is connected to base station. The base station is called here G node B. Okay. You know that it's called node B for 3G, it is E node B for 4G. Now in 5G, it's called G node. The G comes from next generation. The GNOD is connected to the uh, I mean, core network in two paths. So similar with serving gateway, PTN gateway, you have here this UPF and DF. And similar with MME, you have AMF. So basically, it is like AMF. And the other things are like, say, you had authentication center, AUC. Here you have authentication server function, AUC. You have PCRF, you have PCF. So, and there are, I mean, within MME, there are some, there's some functions, okay, to handle the sessions, the data sessions. So that is just shown separately. Now, the base stations, since I mean, it's a time for migration, 4G and 5G. So there are multiple options. Like, let's say it's not here. So you can have say a new 5G base station, but you are yet to be mature enough to get it connected to your core network. So in applicant only it can for or you can communicate with the core network. The data can be routed. Okay, so you're not yet to that stage. So what you can do, you can forward via the present. This is the 4G network, 4G base station eNodeB. Okay. So you can communicate via eNodeB. But if your GNodeB is connected to serving gateway successfully already, then you can of course. These two options fall in the category of non-standalone base station. Another option is standalone. So in that case, both the control signaling and the data routing, okay, are supported in this case to both GNodeB and eNodeB cases. So I mean, you have here all GNodeBs. You're not combining with eNodeB, and so you have, I mean, full-fledged support. But this one is a NG eNodeB, indicates a 4G eNodeB, but it has been upgraded. Okay. So GNodeB means you set up a fresh 5G node. But if you upgrade your present 4G eNodeB to 5G base station, okay, which is GNodeB. If you upgrade it, then it is called NG eNodeB. So whether it is of that type or a pure 5G base station, you are connected using both control and data link for every base station. The protocol stack is the same as we have for LT. The only difference, the control plane protocol stack I'm not showing because it is exactly the same. For data or user plane, there is a small difference. Now in the layer 2, layer 2 already had 3 sublayers. Now the fourth one has been added. It's called SGAP. Fourth one has been added. The purpose is to handle many different QoS, the different radio bearers, different QoS are handled by SGAP layer. So just because 5G has now diverse. RC states are like uh, uh, LT, but with the difference that now there is an additional state called RC inactive. The purpose is to have better power saving. Okay. Although we know that there are DRX cycles possible even in RC connected state, but these DRX cycles are not enough efficient. You have long cycles and that saves some power, but the cycles are not too long. So when you feel that, okay, you can put it in dormant mode to save more power, then you use RC release. Normally RC release moves from RC, I mean, info LT, RC setup. This procedure takes it to RC connected state, and RC release moves from RC connected to RC idle state. In my book, if you look at chapter 14, you can see the procedures for all this RC setup, RC release, RC re-establishment. Now, but if you use RC release with something called suspend, okay, then it will move to RC inactive state, a new state available in 5G. And from there, you can actually quickly move to RC connected state using RC release and with resume option. I mean, the resume option, you can quickly, suspend option, the network can put you in. So, but if you, I mean, the problem from RC, in RC idle state is that you need to go through the whole RC connection setup procedure to switch to RC connected state. So the network doesn't like to put you in idle state when it feels that there's a long gap. So inactive state will help you in this type of situation. If it seems that there will be a long gap, but quickly there you need to establish, then you can preferably use as inactive state. In this state, you what do you do in RC idle state? I mean, you use some paging. Okay, there are base stations in the area covered by TI list. Okay, sense page using STMC, if you remember. Here it is the network similarly looks for you because you don't update the network just when you change yourself. No, you don't do that. Rather, you update when you change a larger geographical area. Okay, so like ideal state. So power saving will then be like ideal state, and that area is called uh, radio notification area. RAN notification area. RAN notification area or RNA. So if you move to another RNA, then you update. So it's all about inactive state, RC inactive. Then you update. But if you need, if the network looks for you, then it uses something called ident in the paging message. Okay. It's not STMZ or CRNT. You're in between somehow in between. Now see, we showed QCI before, but here we have many more levels, right? Because we have diverse applications. So this one and this one. So like this one. and 5. These two you need for voice. Okay, then EV capabilities. The EV capabilities are when you first power up, you inform the network about your capabilities. I mean, in early technologies also, early generations also do that. But here, when you you indicate this way. It can be either 5G type or 4G type. So you support I mean, these things only say 4G, or you support both 4G and 5G. So you just indicate which among these lists are supported. And you send the network will ask you for information. Then you need to send your capability. What can be the maximum data rate supported? Well, very easy to calculate. Like you have, and it's in Mbps, so 10 to the minus 6. Now, whatever you calculate, you can have carrier aggregation, right? Number of carriers. So 20 megahertz plus 20 megahertz plus 20. So you sum up on the carriers. So the maximum capability for a UE. The number of layers you multiply. This means the number of layers generated by spatial multiplexing in MIMO. With spatial multiplexing, MIMO feature, you can have multiple layers. So you can have actually, in practice, you can have 2 or 4. So modulation order, I mean, it can be, say, if J is 3, no, sorry, not J. If M is 3, then I mean, so, for H it is 3. So the number of symbols, the number of bits you have in a symbol is indicated by UN. And you have the code rate. Okay. The code rate. Here's some overhead. Well, say there are some symbols which are used for other purposes, control purposes, or something for channel estimation, like cell specific reference signals. When you are currently, you may be using downlink data transfer. So all resource elements are not used. Some are used for resource channel propagation. You need to leave them out to calculate the actual data. Some overhead. And the number of bits divided by the symbol period. Anyway, I mean, the number of resource blocks and then the number of carriers. Probably we have explained. So if you use them for calculation, you see that the maximum data rate looks like this. I'll tell you later what frequency range 1 and 2 mean. In addition to FDD and TDD, there are also options that you send data only in downlink or only in uplink. FDD and TDD have bidirectional data transfer. But if you have, say, for mobile TV or something, you need only data transfer in downlink. So these options are also available in 5G. That you can have configuration for only data transfer only in downlink or only in okay. Frequency range 1 and 2 just signifies two bandwidth, two range of frequencies in which you can operate now. In the current specifications, two frequency ranges are. Although the actual 5G supports up to 100, but what you have currently available is actually up to 52.6. Two ranges from 450 to 6, which was also available in early deployments up to 4G. In 5G, you basically have frequency range 2 added. Okay, so far.
Sir,
Yeah.
Maghrib prayer is
right.
yes.
So we'll wrap up now. If you have any questions, inshallah, we'll answer them tomorrow. Okay, jazakallah for your time.
Sir, can you upload today's lecture recording by tonight?
Inshallah, I'll do it.